Start. Uh, Hello everyone, welcome to QFT seminar. Today we have Ising from Harvard University. We'll talk about solving lattice QFT with convex optimization. Over to you.
All right. Thank you very much for the invitation to speak. I sort of chose a kind of a general title, mostly because I want to convey the message that the method I'm going to discuss in this talk is very general, even though the concrete results that I will report in this talk are just going to be about the Ising model on the lattice. Now, I should say that I'm just So I'm going to be talking about this paper from a couple months ago, actually maybe 3 months ago, with 5 co-authors on called bootstrapping the Ising model on the lattice. Now this is along the line of what's nowadays often called the matrix bootstrap, really, which really started with the work of Anderson and Kuczynski. Back in, I think, 2016, where they started thinking about solving lattice Yang-Mills theory in the planar limits using loop equations plus positivity conditions. And but at the time, I would say that from their work, there's some promising results, but it appeared that it was difficult to push these numerics to kind of beyond the what they did, mostly because the numerical algorithm was not very efficient. It was not a convex problem, but this paper, as far as I understand, inspired later work of Henry Lin on the so-called matrix bootstrap, and then the following work by Hartnell et al. On the quantum mechanics bootstrap. The funny thing is that, in fact, this method, once again, I want to emphasize this method is very general. In fact, a classical version of the so-called quantum mechanics bootstrap has already appeared independently by the work of Gluskin et al. In also around, I think, 2015, 2016. It was unknown to the bootstrap community in sort of because he studied dynamical systems. But what he did is to use semi-definite programming to study time averages of classical dynamical system, which is nothing but literally the h bar go to 0 limits of the quantum mechanics bootstrap. But then there was a major technical improvement about close to a year ago by Kazakov and Zheng, in which they introduced this relaxation method and turned the loop equations for the planar Yang-Mills theory into a linear system of inequalities, and that allows one to implement these efficient convex optimization methods. In fact, I actually learned this work from Volodya at the beginning of this year for his talk at KTP, and they got very excited. And then a few of us figured that we could actually also just apply this to the Ising model. The point is that the method is very general. It does not really rely on planarity. And so for the rest of the talk, I'm mostly going to focus on the examples of Ising model to illustrate how this works. But as you'll see, it applies to any lattice gauge theory. It's a matter of being, improving the numerical efficiency and being clever. But it basically turns into, solving lattice gauge theory into an engineering problem. Maybe just as a kind of a philosophical point I like to make, I think, when as a student, I was often kind of told that, in physics, in order to solve a problem, solve a theory, you need symmetries in conservation laws. Unless it's a theory is integrable for some reason, you can't expect to solve it. But I think one of the lessons we have been learning from both the conformal bootstrap and other versions of bootstrap is that we can do better than that, and we don't necessarily need symmetries because for most purposes in theoretical physics, to solve a problem, if you have a algorithm that converges to the exact answer, that's often good enough for our purpose. And the way that you would try to find a approximation of convergence to the exact answer may not necessarily be something simple like power series expansion, but it could be something like convex optimization, where you have some let's say a cutoff parameter could be the size of matrices and so forth. And as you increase this parameter, the result will converge to the exact answer that you're expected to get. And depending on the rate of convergence, this may be this kind of approach may be as good as any alternative approach, like a convergent power series expansion. It seems to me that a large class of lattice quantum field theories, at least for certain kind of observables, would be amenable to this kind of approach. Okay, so now anyway, let me get to the actual theory of interest. So let's consider the.
Sorry, yeah. Knowing nothing about this, does this also apply to problems which in the conventional treatment would have a sign issue?
That's a good question. That would be tied to positivity. As long as I would say, as long as you can come up with a useful notion of positivity, I don't think the sign issue will necessarily be an issue. But there'll be let's postpone this discussion toward the end when we have some concrete models in mind. That's a very interesting question. So okay. In fact, one could discuss this already in the situation of some variation of the Ising model, say the Li-Yang model. When you have some imaginary magnetic fields, you have a similar issue as the sign problem. Let's discuss that in a bit later. So the subject of interest right now is going to be the most standard, the statistical Ising model. Which is not to be confused with this kind of a quantum spin chain type model, which which would potentially also be amenable to the similar approach. But I'm going to focus on the statistical mechanics version. So we're talking about d-dimensional lattice, and this lattice will be the from the quantum field theory point of view. Will be viewed as the discretized version of the Euclidean space-time. And of course, in the original Ising model, we're considering a ensemble of spins on the lattice in thermal equilibrium, and we're only going to be interested in thermal averages. By convention, I'm always going to absorb the so-called temperature of the model into the coupling by rescaling of the coupling and parameters. So instead of talking about the high temperature versus low temperature, I'm just going to talk about strong versus weak coupling. It's the same thing. So as usual, the partition function is going to be so we have sites labeled by x in this lattice lambda, and we have spins. On each side, which I take to be plus minus 1. And as usual, we have some nearest neighbor interaction near sites. So in this x and y bracket means they're nearest neighbors on the, let's say, square lattice, but we can one could in principle generate this to other lattices, honeycomb, whatever. But I'm going to be considering the square lattice in 2D and cubic lattice in 3D. So you have nearest neighbor interaction with some coupling J, and I'm going to be focused on the ferromagnetic case. So J will be taken to be positive. That's the sign that will contain a critical point that has a field theoretic limit. As well known, will be described by a conformal field theory at a critical point. And then I'm also going to consider the possibility of turning on a magnetic field. because of course there's Z2 symmetry, and but without loss of generality, we can assume the magnetic field to be non-negative. So and we're going to be, of course, interested in expression values of a product, a set of product of spins. So I'm going to use this notation. So A is a finite, let's say, finite subset of points.
Sorry,
in
isn't there a minus sign in the exponent? There should be a minus.
Nope. This is the Fermat-Ising model. If you wish, the Hamiltonian is negative.
But isn't this going to diverge? If you sum over the path integral?
As usual, the expression values is going to be defined by cutting off the lattice at some finite size. You take the expression value of some insertion of spins, and then you remove the limits, and one can prove that this thermodynamic limit is well defined. Right? I mean, that's the mathematical definition of the Ising model. I mean, you can redefine the measure. You can renormalize the measure if you wish to make it well defined. But of course, as usual, in the physicist sloppy notation, whenever we write the partition function as this kind of sum, what we mean really is that we're interested in expression values, which will be defined by this, with the same thing with the insertion, with all this e to the etc. And with the infrared cutoff, and then you take the expression value, and then you remove the cutoff. Okay. Any other questions?
No.
By the way, I should say that this is actually quite important, because in the Ising model, there are these important inequalities, including the so-called Griffith inequalities that I mentioned later on, whose proof requires actually performing the sum and arguing that terms in the sum are positive, and therefore the entire sum is positive. And for this argument, it's very important to first regularize the system by cutting off the lattice size, and then take the limits carefully. Okay, so but this can be done. All right. So anyway, I'm going to be interested in observables that are these spin expression values. So have an insertion of a bunch of spins on the lattice, and of course, as is well known, there's going to be a critical point. There's a critical point, which is J equals some critical value JC that's positive, and H equals 0. So near the critical point, we have a quantum field here, and that's of course from the field theorist point of view, the limit of most interest. In this limit, the spin correlators at long distances will give rise to, in this case, multi-point correlators of local operators in the corresponding Euclidean quantum field theory. But most of what I'm going to discuss does not specialize, does not rely on being near the critical point. In fact, as you'll see, the actual numerical results are so far going to be the weakest at the critical point, which is not surprising. But they're the weakest at the critical point, but they're still non-trivial. And the hope is that with eventually in the near future, when we improve the numerical efficiency, we'll be able to say something useful about the critical points. And I should say that the approach I'm going to discuss is completely orthogonal to the conformal bootstrap. Here, I'm not going to assume any kind of emergent conformal symmetry whatsoever. And the hope is that the results obtained this way, if you can really say something non-trivial about critical points, will be complementary to the conformal bootstrap approach. For example, in this approach, one can hope to directly access multi-point correlators, whereas in conformal bootstrap, you start with the simplest OPEs and 4-point functions and so forth. It's not so easy to directly approach higher point correlators. Okay, so this is of course this model is known for many decades, and there are going to be two pieces of recipes, each of which is actually completely well known. The only kind of a new thing here is how we combine them, and using efficient numerical methods. But let me review these two pieces of essential ingredients. The first is what one can call the Schwinger-Dyson equation, or loop equation in context of lattice gauge theory. This is not lattice gauge theory, but nonetheless, one can call this the loop equation. But more appropriately in this context, we can just call it the spin flip identities. So these things are actually, even the Ising model context was well known for many decades, because people try to come up with various clever way to solve the model to the extent one can. By the way, I should mention that, of course, as is well known, the 2D Ising model at 0h at the vanishing background magnetic field is known to be exactly solvable. We can come up with a very non-trivial but completely explicit kind of determinant formula for spin correlators. But the 2D with a non-zero magnetic field is not exactly solvable. So in fact, if you start at this critical point for the 2D Ising model and go a little bit away from JC, as well as turn on a little bit of magnetic field, then you arrive at the so-called 2D Ising field theory, which I would say is actually the simplest non-integral quantum field theory. It's a very rich theory, has a non-trivial particle spectrum with the I mean, if you can use the Lorentzian signature with non-trivial S matrix and so on and so forth, it's a very rich and interesting theory. More generally, for the Ising model on the lattice, at non-zero magnetic field, even in 2D, it's not exactly solvable. It's not exactly solvable for a good reason, right? It's not exactly solvable not because we're not clever enough. It's not exactly solvable because we understand that as quantum field theory, when you can go to Lorentzian signature, there's actually particle production. So it's really not an integrable theory. And so in this case, if one can get some non-trivial results, predictions for what the lattice expression value would be, there's actually no exact answer to compare with, but one can nonetheless check against Monte Carlo benchmark, which we'll do. And of course, in a 3D case, the lattice version of the Ising model is not exactly solvable, even though the conformal fixed points now we know a lot about.
See, just a question.
Yeah.
Are these techniques applicable to general vertex models?
General vertex model? You mean what are the models exactly? You mean like a Potts model or things like that?
Yeah, I mean, let's say at a vertex you have certain weight depending on the configuration around it.
Yeah, absolutely. I think you can absolutely generalize these, but I think by the end of this discussion it will be clear. But in fact, some of my collaborators have been exploring a little bit of the Potts model story. But at the moment, I think I would like to still focus on improving the numerical efficiency just for the Ising model, because I think that there's a lot of improvement one can make beyond the work we have done so far. And anyway, we can discuss that at the end. All right. So okay. So the first set of piece of ingredient are these Schwinger-Dyson equations, or the spin flip identities. I'll write that in just a moment. And the second piece of ingredients is positivity. Now, what do I mean by positivity? There are different types of positivity conditions one could discuss. I would say that they are, for my purpose, there are three types of positivity conditions that one can come up with. That are the most obvious ones that one might think would be relevant. One is the so-called reflection positivity. Now, for Euclidean quantum field theory, reflection positivity is essential. It's part of the Osterwalder-Schrader axioms. It basically says if you have some local operator, its coordinate function with its reflection along some mirror plane in Euclidean space, that correlator will be positive. Now, it's not obvious how this will be generalized to the lattice, but given lattice quantum field theory, typically unitary lattice quantum, given typically in the good class of lattice quantum field theories, one can often prove these reflection positivities by hand. They're often not very difficult to prove. And in the Ising model case, we'll prove directly some of these positivity conditions that they will use. So these reflection positivity conditions are the I would say, the kind of positivity condition of lattice theories that have the most straightforward analog to continuum quantum field theory. Even though I should point out that, of course, on the lattice, because you don't have the full Euclidean symmetry, you cannot reflect in any direction you want. There are only a few directions you can reflect in, but that seems to be good enough in our experience. Something else that that one can discuss on lattice is the so-called square positivity. The square positivity is the thing that has been mostly used in the matrix bootstrap story. This just basically means that if you have some real operator, you square it, and its expression value is going to be the negative. Now, this is something that's more or less obvious, but it still has non-trivial consequences. I should say that this actually doesn't have a obvious or continuous continuum quantum field theory analog, at least in the language of the local operators, because to square some lattice operator, we have the insertion of the combination of insertion bunch of operators on lattice sites. To square this is not a operation that is has a obvious and meaning in the continuum limit. And in fact, as we'll see, it turns out, well, I will not show that to you because it's a consequence of doing some numerical tests. But in our experience, it turns out for the Ising model so far, the square positivity was redundant in the sense that once you impose reflection positivity, we'll get all the positivity constraint we need, and the square positivity doesn't actually add anything.
Even though I have one question. Is the reflection positivity property also valid when the magnetic field is non-zero?
Yes, yes, it is. Yes, it is. I will describe exactly what are the reflection positivity conditions I will consider, and we prove that in our paper. These are fairly easy to prove, but they're still non-trivial.
Okay, thank you.
Sure. And then there are
sorry. Is she just someone else? I'm not sure. Okay, Vladimir, go ahead.
Yeah, I wanted to say it's strange that it doesn't bring you much, this reflection positivity, because for young Mills, in our case, it did bring.
Right. Yeah. Actually, yes, indeed. Zhetran told me about that. I don't have anything deep to say. However, I should say that in our experience, this also depends on the region. Seems to depend on the region you choose. With the region where you consider the collection of possible spins inserted in the domain. So it seems to be, at least for the specific shape of these domains, like of the diamond shape that were considered, reflection positivity gave all we need. But it could be that for some other shape that the square positivity will give independent constraints. But eventually, as you increase this domain to bigger and bigger size, I would expect that the reflection positivity would be sufficient. I should make another comment. Actually, you see, I mean, I'm gonna say this in maybe I'm getting ahead of myself, but let me just make this comment now. The results that we're obtaining are supposed to be applicable. We would like to obtain results for strictly infinite lattice, as opposed to something like periodic lattice. You can have lattice with different boundary conditions. You can have periodic boundary condition. Now, naively, something like square positivity would hold also in the identical form on the excuse me on the periodic lattice, whereas the reflection positivity would generally not obviously hold on the periodic lattice. So in principle, there could be, that's what I'm saying. So I could imagine. I could certainly imagine reflection positivity contains all the constraints, but it would be hard to imagine that square positivity would imply reflection positivity. Okay. And anyway, this is just some very elementary comments.
Sorry, this is very minor.
Yeah.
Make sure square positivity.
Sorry, I lost you for just a second. Could you repeat your question?
No. Square positivity is for Hermitian operators, right?
Yes.
Okay. Sorry.
Yeah,
Go ahead.
Yeah. Okay. And then there are
But
a
in
third.
reflection positivity, what is being reflected?
What is being reflected? A arbitrary linear combination of spin insertions on one side, on half of space. I'm going to describe this later, but you know, let's imagine on the plane you have insertion of a bunch of spins over here, but generally linear combination of these, and you just reflect, you know, in this way, roughly speaking. But I'm going to come to this in a bit more detail shortly.
And vice versa, the other side goes to the other side. This side goes to the other side. The blue side goes to the red side also, right?
No. I mean, you know, I take linear combination of these red spins, and that's one operator, and I have a reflected one on the blue side. That's another operator. I take the product of these and take expression value, and that expression value is non-negative. That's reflection positivity, roughly speaking.
Okay.
Okay, good. And the third type of inequalities are the I'm going to be considering or are going to be relevant are the Griffith inequalities. It turns out that they can help with improving the constraints, but they're not too essential. And I'll characterize exactly what they are in a moment. And I should say that these are by no means the only known inequalities. There are many other inequalities that people have derived from the Ising model. But my guess is that these other inequalities, while they might, if you implement them, they might improve the efficiency or improve the convergence of the numerics. My conjecture would be that the reflection positivity is actually all you need. So this reflection positivity is the most essential one in our analysis so far. Okay, so let me now describe in more detail what these first of all, what are the spin flip identities? What do they look like? This is very easy to derive. Basically, the spin flip excuse me, the spin flip identities. These are just derived by looking at expression value and thinking of, like in the language of path integral, you know, you're summing over this spins, and you just do a change of variable. You change. So let me. So this is sum over this spins with this weighting factor, and you consider change of variable. Change variable of you pick some x in the lattice. This x could be either in the subset A, where your spins are inserted in the correlator, or maybe not. And you change variable by flipping s of x to minus of x, minus sx. Let's say if x is not in A, of course this does absolutely nothing to the correlator. But when you do the change of variable, you are changing the coupling in the exponent. So in this case, you would conclude that SA expression value is the same as the old expression value of the same as A, but because you are flipping some couplings in exponents, you have to compensate for that. So you have e to the minus 2j. Let's say the let me call this z actually. Sorry. Let me call this point z, not to be confused with x. So here I'm talking about whether z is in A or z not in A. So then you have sz with this nearest neighbor. So let's say as x, where z and x are nearest neighbor, then minus 2h sz. Okay, this is in the case of z not in A. This is more or less obvious. And if z is in A, then you have a minus sign on the left-hand side. So putting this together, I could write this as 1 minus 2 chi a z. This chi a is a characteristic function where it says this chi a. Z is equal to either 1 or 0, depending on whether z is in A or z not in A. So that's it. So these are very elementary. Now the point is that A is a finite set, so this is some basis of well, this is just some finite collection of spins inserted. I want to consider the correlator. The right hand side can also be expressed as a excuse me. The right hand side, even though it looks like this kind of exponential, but in fact it can also be written in the form of a sum of finite many terms, where each term only involve finite many spin insertions. Because these spin squared to 1, so these are very simple objects to manipulate. Now this is kind of a big mess to do by hand, but it's not very hard to implement this on computer. You can generate these loop equations. Just as an example, let me show you a slide. So this is for the 3D Ising model. This is a very simple case of generally depending on the subset A you consider and the point Z you pick, you can get arbitrarily complicated spin flip identities like this. This is just one example, just to show you what it looks like. Each of these boxes with the dots inside the box is a pictorial representation of a spin correlator. So this is this box, I guess here is a 3 by 3 by 3 box. Okay, so so in this case, in each box there can be this was for the 3D Ising model at 0 magnetic field. So in this case, because of Z2 symmetry, we only need to worry about even number of spin insertions. So for example, some of the boxes have 2 spins, some have 4 spins, some have 6 spins, it's not it's maybe a little hard to see exactly which dot is at which side in this 3 by 3 by 3 box, but this is not so important. Just to show you the general form of this equation. And this A1, sorry, this A2, A4, A6, and B1, B3, B5. These are some coefficients that are functions of J, which you can easily derive from the general form of the equation that I wrote earlier. Okay, so these things are quite explicit. So now let me come to the positivity condition. Oh, I should say one thing. Let me make a few comments about these spin flip identities. The point is that these equations are linear. They are linear constraints that can be written in the general form of sum over S, let's say B, some coefficients A, B. So I started with the set A, but I look at the things related by this spin flip. So they're linear constraints of this form. So this is in contrast to, let's say, the loop equations for lattice Young-Mills theory, which are in a planar limit, which are a priori quadratic equations. In this case, because we're considering all possible spin insertions, they're just linear equations. But the point is that, of course, there's a ton of spins, and in practice, what we're going to do is that so we've got this lattice.
Sorry, this variable Z, there is only one, or there are multiple?
There's only one at a time, but that's exhaustive. But by considering all possible A, subsets A, and consider all possible individual points of Z, these cover all the possible change of variables.
Okay, but one at a time, right?
One at a time, yes, but at the level of these equations, sort of by definition, right? I mean, I started with the set A. I do one flip, but now if you want to do 2 flips, you can get the same equation by starting with a different set.
Okay.
So in general, the expectation value of a generic Ising model can be solved by some mean field theory methods, right? I mean, can be evaluated by some mean field theory methods, and so
you can come up with various approximations, but I'm talking about exact answer.
Yeah, so you're saying that doing some approximation won't help here, because if you do an exact thing, then you wouldn't.
But my goal here is to get the exact answer. I'm going to describe numerics that will, in principle, the hope is that will converge to the exact answer. Having some approximation is not enough for my purpose.
Yeah, but I mean, as you just showed in the pictures, you can evaluate these things only for very small lattice sites, right? Is that correct? I mean, very few lattice sites. But if you want a realistic lattice,
well, that's up to that depends on your numerical ability. But even for just a few lattice sites, the results I'm going to describe are still going to be the inequalities I'm going to describe are still going to be exact constraints on the actual correlator of let's say some neighboring sites, if you wish, in the actual Ising model, and that's not something you can get by
true,
field
but
theory. Yeah,
true, but I mean, are they going to be, say, relevant for some specific model? I mean, if you have some.
What do you mean? I'm literally going to describe the specific model. I'm going to describe exact results for a specific model, namely the 2D Ising model on the square lattice and 3D Ising model on the cubic lattice.
Yeah, and you are going to take the lattice sites to infinity, right? I mean,
the lattice sites are always going to be infinity in my purpose, and in fact, we have explicitly verified that our bounds are tight enough to rule out the possibility of to rule out the results on a periodic lattice, let's say, for some small periodicity, say 5 by 5. You can look at the exact results, and that's actually ruled out by the bounds.
So you're going to take a 5 by 5 periodic lattice and then extend
no,
it to
I'm saying that if you take the 5 by 5 periodic lattice and compute the exact lattice sum and get the results, it's going to be ruled out by the inequalities we have derived.
It's going to be ruled out by the inequalities.
It's going to be ruled out because we are talking about results for the infinite lattice.
What does that mean? What does that mean if they're ruled out by the inequalities?
The inequalities we're going to derive are going to be constraints on exponential values on the infinite lattice. If the constraints are tight enough, they're going to rule out the results on the periodic lattice, which is what we did.
So your goal is to rule out some of the lattices. Is that right?
The goal is to solve the model.
Solve the model.
Solve the model in the sense that you have an algorithm that produces numbers that converge to exact results. In this case, we'll come up with the two-sided bounds that will conjecturally converge to the exact results. That's the goal. That's what I mean by solving the model.
May formulate it slightly differently. That in say Monte Carlo methods, your infrared cutoff is the size of the lattice. Whereas in these methods, like Bootstrap, your infrared cutoff is not the size of the lattice, but sort of the size of your constraints, which you impose on the size of your observables, actually, which you study.
Well, I think it will be. It's not entirely fair to call that the infrared cutoff because Volodya, as you know very well, I mean the results we're talking about here are going to be constraints on the exact correlators. Now,
absolutely,
there's
the
issue of what correlators you can probe. So there's going to be a limitation on how big, what's the size, the lattice size of the operator you can probe. But whatever operator you can probe, the results we're going to claim are still going to be applicable to the strict infinite lattice limit.
Sure, no question. The results are exact in the sense of inequalities, but say the spread of this inequality can be viewed as the result of the size of maximal size of your operators, which you study, yes, which you which are involved.
But I mean, I would just say that at least conceptually, that's different from what we usually mean by infrared cutoff, because usually what we mean by infrared cutoff is a modification of the theory, right? It's a modification of the model that makes some observables better defined or whatnot. But
I want to stress the phenomenon that that's how the length, the infrared length scale appears in this kind of method.
Sure.
We can call it.
There's no free lunch, but
we can call it by any name, but that's what it is. Okay, thank you.
So anyway, let me proceed. So our strategy is going to be that we're going to pick some of course, to implement this numerically, we have to work with a finite system. But the lattice is going to be strictly infinite, as I have been emphasizing. When I say finite system, I mean a finite system of correlators on the infinite lattice. So I'm going to pick some domain. Let's say this is my domain. Let's call it D. The D consists of some lattice points. The reason I want to pick a domain is just to say that I'm going to be looking at, when I say a set A, the A could be something like this. So this is my A. So A, because I've been talking about this this correlator of SA. So A is some. So I'm going to fix my finite domain D in the infinite lattice, and A is some collection of sites within the domain D. But I'm still going to be interested in experience value of SA on the strict infinite lattice. It's just that in order to I have to truncate my system of equations, but this I'm just going to look at a subset of equations where A only belongs to D, and I'm also going to take the so I'm going to do this spin flip at the point Z, for example. I'm also take the Z to be within the domain D. In fact, I'm going to take the Z to be Z could be anywhere here or here or here or here, so that if you do the spin flip, it's going to involve the insertion of neighboring spins to the point Z, but we don't want it to spill out of the domain D. Right. So as long as you take Z to be one of these green sites, then doing the spin flip, you'll get spin flip identities that involve correlators that still lie within the domain D. Okay, so this equation closed within a set of correlators within the domain D, and that's what we're gonna be dealing with. Okay, so now, of course, if you want to probe long distance spin correlators, you want to take the domain D to be at least big enough to cover that domain, and then numerically that's going to become more expensive. So for now, we're just going to be focused on short distance correlators, but I want to emphasize that these are still results going to be results for the strictly infinite lattice. Okay, so now let me describe the reflection positivity conditions. Oh, I realize that I'm going very slowly. But how strict is the time limit?
No, I think you have sometimes. So yeah,
okay.
Yeah, usually the seminars are long.
Okay. So let's, in fact, but still, I think in view of time, let me go to the picture that I already have here instead of trying to draw them by hand. So okay, I guess this is the picture that I showed earlier. So in the case of the 2D Ising model, I'm going to refer to this as the 13531 diamond. It's a diamond shaped region. I'm counting as one horizontal number of sites. Okay, and this orange stuff here is a smaller domain, which we can also consider. We'll call this orange one the 131 diamond. And I'm going to later present results based on these spin flip identities as well as the positive conditions for correlators restricted within these domains. Let me now describe the reflection positivity. So reflection positivity for the Ising model on the square lattice. We can also discuss the cubic lattice, but for simplicity, let me just focus on the square lattice here. There are actually 3 different types of reflection positivity. First of all, as I already mentioned, because the lattice break the rotation symmetry, you cannot reflect in arbitrary direction. You can reflect horizontally or vertically, or you can reflect diagonally. Okay, it turns out that there are 3 distinct types, and no more as far as I can see. So you can reflect either along this is in 2D, along a array of let's say vertical lattice sites. You can do that, or you can reflect on a plane in between, or in this case a line in between 2 arrays of vertical lattice sites. They are different. Okay, they are not equivalent. You can also reflect diagonally, but in this case, you can only reflect along the diagonal set of lattice. You cannot do something like, let's say, if you want to do this, it doesn't work, actually. At least I couldn't prove any non-trivial reflection positivity conditions if I reflect along this orange diagonal one, because they're actually, they're not quite, well, anyway, if it, if you can prove something related to that, that'll be interesting to know. But so far, I haven't been able to get anything out of that. So let's not worry about that. But even for these, actually, it's not totally obvious because if you want to, so how do you prove this kind of reflection positivity? You basically want to write the correlator. So you have some operator inserted on one side, let's say call it O. On the other side, let's call it O reflected. And basically, you want to write, the idea is that you want to write the correlator as some kind of integral over some, well, not integral, in this case, some sum over, well, let me actually not write formula for now. You can look at the formula in the paper. In the path-integral language, you'll be like writing this correlator as integral over wave functionals on the mirror plane, in this case, the mirror line, of some integrand that is a square of something, right? So you have O on one side, you have the reflected one on the other side. So they're both functionals of some set of spin variables. It's a square of something. But in this case, actually, it's a bit more subtle because you have actually this mirror line here cuts across these links. And so actually, you have some spin variables, let's say you have some S variables on one side, you have some S prime on the other side, and you have some coupling e to the j s s prime. You have some e to the j s s prime. So roughly speaking, you can say that we have some wave function of the spins s on one side. You have some wave function of the spin s prime on the other side. But then you also have this this coupling coming from the links, and you are kind of integrating or summing over this s and s prime. And it turns out that in this case, in order to prove this reflection positivity, we have to assume that J is positive, or J no, we have to assume that the Ising model is ferromagnetic, and in fact, as far as I know, if J is negative, this kind of reflection positivity actually fails in this case. But that's not a problem. We're interested in the ferromagnetic Ising model, and we can prove this reflection positivity in this case, and that's good enough for our purpose. Okay, so these are so this is reflection positivity, and let me just mention briefly that I should say that just in this discussion, even though in the picture I only drew some specific insertion of spin, I want to emphasize that this O is not just a product insertion of spins. It's a sum. It's in a combination. So it's a sum of some coefficients, and this S A, where A belongs to half space, half space, or half of the lattice. Okay, and in particular, say in the first case where the reflection plane or the reflection line contains some lattice size, we also allow these operators to spill over to the plane itself. Okay, as I mentioned, there are these square positivity, which is just of the form O squared, negative, where O is again the sum of some combination of the speeds. And then there are these Griffith inequalities. So what are these Griffith inequalities? So for our purpose, we'll consider two different Griffith inequalities. One is the statement that all the moments are non-negative. So these are also, again, applicable to J positive, so the ferromagnetic Ising model, as well as H non-negative. The second one is just it's just a convention, but of course, because of Z2 symmetry, without loss of generality, we can take the magnetic field to be non-negative. Under these assumptions, one can prove these Griffith inequalities. The first one says odd moments are non-negative. For example, a single spin expression value is non-negative if the magnetic field is non-negative. Okay. The second one says that for any subset A and B, SA-SB correlator is bigger than or greater than or equal to the factorized correlator, SA expression value and SB expression value. The second one is slightly trickier to prove, but nonetheless, these are not too hard to prove. And I learned this initially from the book of Glim and Jaffe called Quantum Physics from a Practical Point of View. So these things have been well known for decades, but we included derivation of these inequalities in our paper as well. We'll see that, as I mentioned, we believe that these Griffith inequalities, as well as many other inequalities, are not necessary in addition to the reflection positivity, but they are they can help improving the numerical efficiency. Okay, so now let me describe some results.
But they are nonlinear now. Yes.
Very good. I'm going to comment on this later, but indeed, the second Griffith inequality cannot be straightforwardly implemented as a convex problem, and that's in fact the reason that for the semi-definite programming we actually did not take the second Griffith inequality into account. But after obtaining the results, we can check whether after obtaining these bounds on the spin correlator, we can check whether for the solution that saturate these bounds, the tentative solution that saturates the bounds, whether the second Griffith inequalities are obeyed or not. And it turns out there are cases where it is actually violated, which means that if you do include them, you can improve the bound. Anyway, I think this will be clear when I present the plots. Why is it that you can improve the results, but also that I think actually they are not necessary, in the sense that if you consider larger region, I believe that that you can overcome the lack of including these Griffith inequalities. Okay, so now first let me describe the kind of the regions we work with. As I mentioned, we work with 2D. We have this 13531 diamond. That's what I'm talking about here. We can consider the case with magnetic field or without magnetic field. Without magnetic field, there's a simplification, which is that we can ignore odd number of spin insertions. If you as far as this, the kind of as far as to the extent that if you're interested in the symmetry kind of unbroken phase. Now, for the non-zero magnetic field, of course, it is necessary to include odd number of spin insertions, and the system gets slightly bigger. That's what I'm considering here. And for a three-dimensional Ising model, we can, on the cubic lattice, we can do a similar thing. In this case, I guess I didn't include the picture here, but we can consider, say, I'm trying to draw a picture like this. So, for example, in 3D, if I consider these collection points, these are this collection of 7 points. This is a plane. We contain the 5 points in the plane. So this is what I call the 151 region in the 3D case. And so if I say 1551, it means I just add some layer like this, and so on and so forth. Now, ideally, one would like to consider a diamond of a shape like 1, 5, then 13, 5, 1. But that turned out to be a little bit too big of a system for us to be working with so far, at least in the work we have done so far. But I don't think it's completely out of reach. So that's what we'd like to achieve numerically in the near future. But for now, we're just consider this a smaller system.
One question.
Yeah.
So why do you like the diamonds as opposed to, let's say, just a cubic?
It is the reason for this is that if I do a spin flip at say this point here, it's going to introduce spin insertions in its neighboring sites. So over here, 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 and here. All right. So with the diamond-shaped region, if I if I work with a 13531 diamond, I can do spin flip identity for all these green dots here, and they include the spin insertions of these points. But that's it. If I had chosen a square-shaped region, then there'll be some corners where I will never reach by okay. So it seems like it's less efficient. But and I should say that I think it was the case that if you consider a square region, it turns out that the square positivity may not be completely independent, may not be just a consequence of the reflection positivity, but just in practice, the square positivity has more variables, because you have the spin insertions in the entire region as opposed to half the region, and it was numerically less efficient, and for various reasons of numerical efficiency, we thought that the diamond regions were the best to work with.
Okay, thank you.
Yeah. Okay. So in each of these cases, of course, you would like to take account of the basic lattice symmetries. So this primitive subsets means the all possible choice of subset of points A inside this diamond or some other shaped region that are unrelated by symmetries. So this is the system of these basic spin correlators that will enter the system of equations. Now, the spin flip equations, you get a bunch by taking every subset A in this region, and you do a spin flip somewhere. So there's a ton of equations. It turns out these equations are excessively overcomplete. They are very much overcomplete, but it is not obvious, at least to us, it is not obvious how to identify the linear independent equations. So there are very non-trivial relations actually among the coefficients that allow these equations to actually be redundant. So there are linear relations among these equations, and symbolically, it is very complicated to try to solve these equations, and essentially it's impossible. So we have to solve these equations numerically. The thing is, analytically, symbolically, we actually do not have a way to tell what is a set of independent, linearly independent spin flip equations. It's just a very complicated system, even though it's a very completely elementary problem. And in practice, we have to figure out which equations are independent numerically. But that poses a numerical challenge because you need to solve these equations numerically to sufficiently high precision to be able to tell which equations are independent. If you have a not sufficient numerical precision, you're solving this with, say, Mathematica with not high enough precision setting, you might mistakenly thought a set of equations are independent, even though they're actually linearly dependent. There could be some relations that you will miss if you don't work at high enough numerical precision. But anyway, there are clever tricks one come up with and to overcome this difficulty. But the bottom line is that you need to work at the sufficient numerical precision and be careful enough in manipulating these equations to identify the independent equations. But this can be done. So after doing so, you will find the independent equations, and there's a huge reduction after taking these equations into account, and we have these independent spin correlators. So in the case, for example, the 2D 13531 diamond region, we end up with only 19 independent spin correlator after taking account of these Schwinger-Dyson equations. I should say, however, that the reflected positivity condition, which will be expressed as some big matrices whose entries are linear, right? I emphasize that these matrices their entries are linear because they're still just some correlators like this. So we have some matrices whose entries are linear in these spin correlators. Once you solve these spin flip identities, the correlates are expressed in terms of these independent variables, but these matrices are going to be very dense. So as far as the convex optimization is concerned, we're dealing with dense matrices, and that itself kind of poses another numerical challenge, which is that usually this kind of a convex optimization packages are often quite efficient in dealing with sparse matrices, but for dense matrices, that's the most difficult case. Anyway, and I should say that once we have solved the equations, we can just plug this into these the solvers. It basically reduces to an engineering problem. You just find the most efficient solver that can handle this. We've used a mosaic in a situation where the matrix is not too the number of variables are not too big. We don't need very high precision, but in some cases where we need higher precision, we use SDPA quadruple double precision solver.
One question
so far. Yeah.
So this first example, for example, what is the size of the matrix of inequalities?
Oh, the size of the matrix. That in this case I don't quite remember. But you see, the size of the matrix you can always truncate. Okay, so the size of I think the biggest matrix we have to deal with was maybe around like 1,000 by 1,000. But the thing is, this is not a huge, I would say, a limitation factor, because if the size of the matrix is too big for your solver numerically, you can always truncate the matrix to the first, say 100 by 100. What do you call it? So the principal minor or whatever, you still get rigorous positivity constraints, maybe not optimal, but that's okay.
Okay.
Yeah, so I wouldn't view the size of matrix as a huge obstacle. First of all, because you can truncate it. I mean, in practice, the bigger obstacle is the number of independent variables. That's kind of hard to overcome if you have 1,000 of independent variables. That's when it becomes very difficult for these numerical solvers to handle. Okay. Actually, I guess I meant to give a very elementary example of how this kind of thing works. Maybe I'll just show a very, very elementary example, just for people who are not familiar with this semi-definite programming, to get a flavor of how these things work. Let me see. Let me share this screen on my Mathematica. This is kind of a well-known example, just in the context of matrix bootstrap. In fact, it's just to deal with the integral. So let me see. Let me unshare this for the moment. Let me unshare this for a moment, and let me switch to my laptop. Okay, so can you see my Mathematica file here? That's good?
Yes.
Okay, so I'm just going to illustrate this in an extremely elementary example. This is all the code you need with Mathematica. Okay, so all I'm doing here is I'm computing the integral of e to the minus x to the fourth over 4. Okay, so this is like the the Bessel type integral. So I'll know this. But the point is that you are supposed to view this as a toy model of a path integral, right? This is like a 1-by-1 lattice. In this case, so you have the action is x to the fourth here, and we're going to be considering expression values of x to the 2k. So these are the moments. Okay, so the expression values, I'm going to call it wk. So these wk's are the analog of my spin insertion expression values, right? Okay. So and I can normalize the identity expression value is just 1, and the loop equations, or the Schwinger-Dyson equation in this case, you can easily derive by changing variable, is just a relation of wk to wk minus 2. With some coefficients, you can easily derive, so you can easily solve these equations. You can solve everything in terms of w1, which is the expression value of x squared. Okay, so after solving the loop equations, you express all the moments in terms of w1. and then you're going to have positivity conditions. So let me just show you this very quickly. So you can run this, and you solve all the w's in terms of w1, right? And then in this case you have the square positivity. So this ww, this is the matrix of square positivity. You can take a look at what it looks like. I take some arbitrary cutoff L. So it's a truncated version. L is 15, so I keep up to W15, and I get this matrix. This matrix is supposed to be positive semi-definite, and I've solved all the entries in terms of W1. Okay, so that's the matrix that's supposed to be positive, and then you can just use the method. In this case, this system is small enough. You don't need any fancy solver. You can just use Mathematica semi-definite optimization. You can minimize either minus W1 or W1, in which case you get both the upper bound and lower bound on the W1, which is the x squared expansion value, with the input, with the subject to the condition that this matrix WW, this is the square positivity matrix, has to be positive semi-definite. Okay, so you just solve it. It literally takes a second. It gives you the answer, and you can compare with the actual integral. The Mathematica can do it numerically, and you see that it agrees. Okay, so that's it. So the rest is then to generalize this so you can generalize this obviously, as you can see, to the Ising model as I have described. Okay, so now I'm going to switch to let me see. Actually, how do I unshare this? Oh, wait. Actually. How do I unshare this? Oh, stop share. Okay. Let me. Okay. Now let me share screen on the my iPad again. Okay. So now let me present the actual numerical results. Now that you have an idea of how this numerics works, but you have to use the more complicated solver on cluster. So this is a plot of the nearest spin correlator on the 2D. So this is 2D Ising. This is 2D Ising on the square lattice at h equals 0. With the where I'm considering the nearest spin correlator. So another one, what I mean by S0, SE1. So 0 is like the origin of the lattice. E1 is the unit lattice vector in one direction. So this is just the nearest spin correlator. This is the simplest non-trivial thing you can consider in this example.
Oh, sorry, one question.
Yeah.
This correlator could have been in the 3D Ising model as well, right? I mean,
well, the 3D Ising model, the answer is different.
The equations that you would impose is just a subset of
no. This is not the same set of equation, because in 3D, if I flip a spin, all these neighbors, it will involve insertion of spins on all of these neighbors.
It is
so
not
the coefficients are very, it is very different. It's very different. As you can see, in the 3D case, the equation is much bigger. Yeah.
Okay.
Yeah. Okay. So so in this example, so this is the simplest non-trivial correlator on the 2D Ising model, so this is plotted as a function of J. We can get both upper and lower bound, as you can see in the earlier toy example. By this semi-definite programming, we can obtain both upper and lower bounds on this correlator. Okay, so not surprisingly, so this is, for example, it will be the upper bound. This will be a lower bound. For this dotted gray line, this is based on the 131 diamond. So this is a very, very small diamond, and from that 131 diamond, you can get this this very crude bound, which are non-trivial, but if that's all you got, it will not be very impressive. But it turns out that if you go to the 13531 diamond, you already get a much tighter bound, which are these blue dots for the upper and lower I've shown here. And in comparison, the black one, the black one here, this is the exact result, because this case the model is solvable, so we know the exact results. You can compare it, and then of course it's in agreement. And you can see here that while at the critical point the bound is not terribly strong, but still is very non-trivial, it quickly tightens as you move away from it. In fact, because it's kind of hard to see how big a difference is, to quantify this, here we can see a plot of the actual difference. So let me unpack this a bit. So in this plot, so I'm looking at the same plot, but I'm taking the upper and lower bounds based on this 13531 diamond region, and I compare it to the exact result. So that's what I call the difference. All right. So if I compare the exact result to the lower bound, right, you can see that the exact result is very close to the lower bound when J is, oh, I forgot to say that this is JC. So if the exact result is, if you compare to the lower bound, it's very tight below JC, for J below JC. So this will be the high temperature phase, and J above JC will be the low temperature phase. And the low temperature phase is a little worse. So indeed, you can see that for the blue dots, this is the difference between the exact result and the lower bound, and it tightens very quickly for J below JC. So this is, again, is JC, and it's a bit loose when J is above JC. In fact, it tightens so quickly that when J is below JC, like when you go away for some amount, it actually, let's say over here, it becomes actually tighter than the result you can easily obtain with Monte Carlo. So here I'm comparing this to the benchmark of Monte Carlo era with the Metropolis algorithm. In the Metropolis algorithm, one usually the computing time is counted by this number of sweeps. So here I have included the Monte Carlo error analysis. This is the 1 sigma error bar based on 10 to the 4 versus 10 to the 6 sweeps. Now, because of the Monte Carlo error has this inverse square root law, so this is a logarithmic plot. If you want to go beyond this, at least with a standard Monte Carlo algorithm, the computer time, it's very hard to improve this dramatically, because there's a hard limitation on the computing time based on the resource you have. But you can see, compared to the Monte Carlo, actually the bootstrap bound, at least if you move away from criticality, it tightens exponentially. So the bootstrap or this optimization or bootstrap approach is very, very efficient away from criticality. Of course, it's worst at the criticality, but there's still a lot of room to improve. There's also this other plot of the difference with the upper bound that has the opposite behavior, that is much tighter and for a larger J or the low temperature phase. Okay, so this is the most basic example. Let me show you some other things you can explore. For example, you can look at single spin expression value. This is just going to be the upper bound. This is, again, in a situation with the magnetic field set to 0. So this is a probe of spontaneous magnetization, right? So in fact, again, because in this case the model is solvable, so the exact result. So this is the exact result. This black curve here. You can see when J is above JC, that's when you can have spontaneous magnetization. So this black curve is the result for spontaneous magnetization. Of course, below JC, there's no magnetization, right? This this optimization, this convex optimization based on positivity knows about that. So here, this plot, this as you can see here, this kind of the crude version of the bound. The crude version of the bound is based on the 131 diamond. So this is the 131 diamond. This improved bound is based on the 13531 diamond. And here we also have the option. We also tried the option of including the first Griffith inequality versus not including the first Griffith inequality. Remember, the first Griffith inequality says that all the moments are are non-negative. So that's this G1. So this is the statement that all the moments are non-negative. It turns out that, for example, if you in the 131 case, if you include that, a part of this just drops down to 0. But in the 13531 case, if you include that, the first Griffith inequality, you also have some very small improvements, but not very substantial. Okay. Now let me show you. Here's the plot where we do include magnetic fields. So this is again 2D Ising, but now with both J and H. So here's J and here's H. So we have a 3-dimensional plot where we look at the nearest spin correlator as a function J and H. And we're going to plot both again the upper and lower bounds. Now for much of this plot, the upper and lower bound are very close. So for visualization, we indicate the difference between upper and lower bounds with the color scheme on logarithmic scale. So at h equals 0, actually, the difference between upper and lower is still visible. For example, here you can see the difference between this upper and the lower bound. This gap is visible in the plot, but this very, very quickly tightens and soon becomes invisible. Exactly how much the separation between the top sheet and the bottom sheet, which is the upper and lower bound, is indicated by the colors here. So you see the red corresponds to 10 to the minus 1 difference, which is visible at the boundary here, but the blue is 10 to the minus 15. Okay, so in the blue region, actually, upper and lower bound coincide within 15 digits. So this we need a high precision solver to be able to tell. But you see, there's some kind of a funny pattern of exactly where the bound is the weakest. It's kind of along this this red band here, and we have some vague idea on how this on what the explanation of this is actually was suggested to us by Slava Richkov. But in view of time, I will not get into this discussion here. But these are questions one can think about in order to improve the the efficiency or the convergence in the future. So this red band is a region that the bound is the loosest, and that's the we like to improve. Here I wanted to show you another plot to compare against the Monte Carlo benchmark. So this is a plot again for 2D Ising at J equals JC, but non-zero H. So we're looking at this again, the nearest spin correlator as a function of magnetic field H. Of course, we're moving away from criticality now, but we're looking at the difference between upper and lower bound. We just want to see how tight the bound is. And you can see again once here it tightens dramatically as you increase H. While at the critical point it's a bit weaker, but as you increase H, it quickly tightens and very soon becomes far better than the result that can be attainable with the Monte Carlo methods, at least the standard Monte Carlo algorithm, which is not very sensitive to H. And on the right-hand side, this is a plot of comparison of the Monte Carlo result together with the arrow bar to the upper and lower bound, just to see whether the other upper and lower bounds can actually rule out Monte Carlo results. I mean, that is not supposed to, because the Monte Carlo result is supposed to be statistically correct at least, but it's only 1 sigma. And you can see that, so the right-hand side plot, if these bars, these error bars, if they are below the horizontal axis, that means Monte Carlo results actually are ruled out. And you can see in some cases they are actually ruled out, but they're just ruled out by 1 sigma. So it's completely compatible with the expected statistics. And actually, it turns out that if you look at the 2 sigma error bar, I think all these points are going to be consistent. This just shows that these bounds from the upper and lower bounds from the convex optimization are actually very non-trivial, and they are sensitive enough to rule out the Monte Carlo results if you don't have enough statistics. Okay, so here I'm showing you the plot of again at non-zero magnetic field as a function of J. So this is at a small magnetic field versus a moderate, large magnetic field, let's say, for both the nearest spin correlator as well as the single spin correlator. So the second is a probe of magnetization. In this case, not a spontaneous magnetization because I've already turned on the magnetic field, But as you might imagine, if the magnetic field is very, very close to zero, then if the magnetic field is strictly zero, then it's not possible to get a non-zero lower bound. But if you have, if it's slightly non-zero, then if you're in the symmetry, if you're in the low temperature phase, then you expect the spontaneous magnetization. And indeed, you can see, for example, perhaps this is the most. This one is one of the dramatic plots. So here's the upper bound on the magnetization from the 131 diamond region. This is lower bound from the 131. So these bounds are rather weak. But as you go to 13531, 3531, the upper bound is already pretty much converged, at least by eye, to the Monte Carlo result, which is this red curve here. Since there's no exact solution, but you can get this to high accuracy with Monte Carlo for at least by eye. That's good enough. But interestingly, this lower bound based on 13531 diamond is also dramatically approaching the upper bound. So you can imagine that if you include a bigger region, perhaps there's much of this much of this blue region will be gone, and it will converge. This is why this is part of the reason why we thought that the reflection positivity will be sufficient on its own. By the way, I should mention, I'll come to this on the next slide in more detail, but I haven't said anything about the second Griffith inequality. In fact, as Volodya pointed out earlier, that was not obviously of a convex form. In fact, one well-known consequence of the second Griffith inequality is that all of these expansion values, a function of J or H, are going to be monotonic functions. They're monotonically increasing functions. So whereas you see here that some of these lower bounds actually are not monotonic. For example, this one obviously not monotonic, and also here there's this dip. Okay, so that's a little bit weird, but we haven't included the second Griffith inequality, and our explanation is actually that if you do include the second Griffith inequality, you shouldn't have this dip feature. If you're able to include that somehow, and we'll see that a bit on the next slide. But once you increase the magnetic field a little more, these bounds converge very quickly. So on the right-hand side of the plot, where the magnetic field is a little bit bigger, is bigger, the bounds have essentially converged. You cannot tell the difference by eye, but the upper and lower bound both coincide with the red curve, which is the Monte Carlo result. Okay, so now here I'm just showing you a very simple plot that illustrates where the second Griffith inequality fails. So this is a very simple result based on the 131 diamond. This is upper bounds for both the magnetization and as well as the nearest spin correlator. In fact, let me make sure I get the parameter setting here. Yeah, I forgot to say to write here that this is at the magnetic field H equals 0.3. In this case, sorry, actually, I misspoke. This is supposed to be this is the lower bound. Lower bound is the one that exhibits this non-monotonic behavior. The point is this. Let's focus on these. Let's say let's look at this curve here. This is if we impose the reflection positivity on the 131 diamond together with the first Griffith inequality, and it has this non-monotonic feature. So what does it mean to have this orange? What does this orange circle mean? What happened is that for the orange circle, starting here, this is where the second Griffith inequality is violated. So by G2, I mean the second Griffith inequality. So as I commented on earlier, the second Griffith inequality would imply that all these bounds are monotonic. And it's interesting that when the bound actually fails to be monotonic, they also happen to be the place where the second Griffith inequality at least approximately, the second group inequality, you can verify that will be explicitly violated by the solution to the spin correlator that saturate the bounds. So that is to say, if you include the second group inequality, will in principle improve the bound, but it's not obviously a convex problem, and we can discuss how one can incorporate that. But I don't think it's too essential because it seems numerically, if you make the region bigger, you can get improved bounds that just like this thing here, and you don't have to worry too much about the bound being not monotonic. As eventually we still expect it to converge to the exact answer. Okay, so this is now we have a comparison of the earlier plots. This is again at h equals 0 for the nearest spin correlator versus the next to nearest spin correlator. And not surprisingly, the bound gets a bit weaker, but it's still non-trivial and has the same qualitative feature. Now, I mean, of course, if you want to probe the critical point, then one would like to consider a much longer correlator. But that would require working with a larger region, and you have to figure out what is the most efficient region to work with. Maybe not a huge diamond, but rather some kind of elongated, rectangular shaped region. That's something yet to be seen. Finally, let me just show you this plot of the 3D Ising. Because of the numerically this is more demanding, so these results are a bit more preliminary in the sense that. So I should say that so this is again of the nearest spin correlator in the 3D Ising model, and here we considered the possibility of the regions 151, which let me like this. We considered 151 region, which are these orange dots. We considered 1551, which are this orange together with the red, and as well as the 15551, which is this set of points shown in this diagram here. Let me see. I think in this plot, these gray lines, these are the upper and lower bounds from the 151, itself. Right. The brown dots here are for these brown dots here, both the upper and lower one. These are from the 1551 region, and these blue dots here, which are the tightest bounds that we have, are for the 15551. But with the truncated matrices, because the system was a little bit too big for the solver to deal with. So it turns out in this case, when we tried with SDPA quadruple double precision, it was too slow, and we use Mosaic, which has a limited precision setting, and seems to be one runs into numerical instability unless we truncate the matrices to some relatively small size. So in this case, we just truncated these matrices, which would be of the order, let's say 2000, to the first 100 by 100 entries, which are still positive semi-definite, but it's of course by no means the entire set of reflection positivity constraints. But still, you get reasonably, you still get a better bounds than the 1551 case, and that is compared to the Monte Carlo results. Which is this red is Monte Carlo. So as you can see, it's consistent, and again, it shares similar features, but there's a lot of room to improve. So this is the last picture I will show you. Maybe before I end, I'll just briefly comment on the how this kind of thing can be improved. So conjecturally, I would make the conjecture that if you just include reflection positivity, that should be enough. So if you make the diamond bigger and bigger, I would expect this upper and lower bound to converge to the exact answer. There's both the question of whether this is true in principle. One can try to prove that mathematically, which will be very nice. But there's also the more important question, perhaps, is the numerical efficiency. How fast would this actually converge, and is it really feasible for extracting continuum, the continuum limits, and get a reasonably useful estimates on correlates of the quantum field theory, the Ising field theory near the critical points. I don't have a definite answer for that, but the thing is, there's potentially a huge room for improvement of the algorithm, because one might suspect that the reason that these upper and lower bounds converge when you look at these constraints to the positive definiteness of the matrices whose entries depend on these spin variables, one might suspect that the upper and lower bounds converge when when you are just about to violate the positivity. So maybe these matrices have some small eigenvalue that will go to 0 as you take some whose eigen, they will have some small eigenvalue, or some eigenvector whose eigenvalue will go to 0 as you take the region to be bigger and bigger. That suggests the possibility of some kind of approximate null states. Now, in the Ising bootstrap kind of story, one understands that there's a notion of a null state due to the equation of motion, but the equation of motion has already been taken into account in these Schwinger-Dyson equations. So one might suspect that maybe there's some kind of new emergent approximate null states as you make the region bigger. And if you identify what that kind of approximate null state is, it might hugely improve the efficiency, because you will know what eigen vector of the matrix to be looking at, and just to impose that that the matrix is positive, acting on those approximate null states, will give you the strongest bounds. So I think the story is very much at its infancy, and there's a huge room to improve, both in even just a level of software to use the SDP solvers that can most efficiently deal with this kind of problem, as well as the actual additional physics inputs, in particular regarding this possibility of approximate null states. So I think I'll stop here. Thank you.
Thanks a lot. Let's thank him for the nice talk. Any questions?
Sir, I had a question.
I had a question. Sorry, please go ahead.
Sir, in the order 3D Ising models, if we have some missing lattice point, then how can we define then how do we define the reflection positivity?
Sorry, the missing lattice point. What did you mean by missing lattice points? Sorry, there's a lot of noise. I can't quite hear the question. Can someone else hear and repeat the question? I couldn't hear.
Yeah, I think there's a lot of noise. Even I cannot hear the question.
Am I audible now?
Yeah. Yes.
In the Ising model, if you have some missing lattice points, then will that have
why do you say what do you mean by missing lattice points? You mean that my region is not the entire lattice? I mean, I should say that, of course, in this case, I'm going to only look at reflection positivity that's confined within the region, right? I mean, so when we write a computer program to generate this measure, we have to take that into account. For example, in this case, if we got some points here, right? You can reflect to the points there along some plane like diagonally like that, but you cannot go outside the region. But as long as you choose your points so that the reflected points also is contained in this region, then you are fine. So then the system of constraints still close on this set of correlators. Does that answer your question?
Can we find any relation between this and the thermal field double state?
The thermal field. Wait, did you say thermal field double?
Yes, sir.
The thermal field double. I'm not sure what you mean by thermal field double in this context. First of all, I'm not even considering a Hamiltonian system. This is a statistical model.
So if you had to obtain correlation functions, perhaps in the renderer vacuum or something like that, Will there be any kind of?
Okay, but I don't think I have anything intelligent to say so far. I mean, first of all, this analysis is about the lattice model. It's not about continuum theory, right? I mean, you see, the reason that we have to work with the lattice is because these spin flip identities are derived essentially in an essential way on the lattice. It's not obvious how to generalize to the continuum field theory, even though I know that there are people who are currently thinking about it.
Thank you.
I had a question, Shri.
Yeah.
See, if you look at the Schwinger-Dyson equations for the lattice gauge theory, the nonlinear term has lots of possibilities of sign flips, actually, as you know. Now, it was never clear how to take a continuum limit of those equations because of this signs.
I mean, I don't have anything useful to say other than to say that the strategy here is not to take a continuum limit of loop equations, right? The strategy here is to get the actual bounds on correlators on the lattice, and then hope that as you take the continuum limit, these bounds themselves are non-trivial, survive in the continuum limit. So I'm not attempting to take any kind of continuum loop equations. I'm not sure if that can be done. I don't have anything useful to say in that respect.
Yeah, okay. Thanks. I also think that those equations, continuum limit is not very easy to take, or at least looks a bit impossible, actually.
Yeah. But I mean, it's interesting to try to explore that, but I don't have anything useful to say so far. In fact, maybe one thing I want to mention is that, you know, this kind of approach also have not only for quantum systems, but also have interesting non-trivial implication even for classical dynamical systems. So you can imagine studying a discretized version of a Navier-Stokes fluid on the lattice, and you can try to study things like time averages, which are not that different from this kind of expression values. In the context of turbulence of a Navier-Stokes fluid, we're interested in time averages of coordinate functions of velocity at different points. And one can imagine trying to study that using similar methods. But the thing is, we're a bit lucky in the Ising model case because the spin squares to 1, so the number of variable doesn't explode. If you keep inserting spin, if you insert 2 spins on the same side, you just get back to 1. But if you don't have that feature, things the numerics can get a bit hairy. So one has to come up with either like nicer models or some other trick to deal with that.
One question.
Yeah.
First of all, thanks very much for a wonderful talk. So here as you remarked in the middle of the talk, that the results that you obtained are for the infinite model, not for a finite size, and that is because the reflection positivity inequalities that you imposed.
Yes. I suppose actually, if you consider, let me see. If you consider periodic lattice, that's right. It's actually the reflection positivity. I mean, I think because all the other lattice symmetry,
So I was just wondering if there is a way of inputting the size of the periodic lattice somehow, inputting that into the equation in order to obtain the correlator finite.
I would suspect that if you really if you're really interested in the finite lattice and you just want to get that, I want to put in the size, you probably need something that wraps around.
I see.
Well, I haven't really thought carefully about that, but I mean, there are many possible generalizations. But I think there's a lot more work to do, even in the most basic and the most canonical case.
Yeah. Thanks.
Hi, G. Just returning to the question of the sign problem. Now, you use mainly reflection positivity, which is the translation of unitarity to Euclidean space.
Yeah.
And even models with the sign problem can be unitary. So
That's right.
So it sounds like you could go ahead and do simulations and that people who do Monte Carlo cannot, right?
It's yes, I think it should be possible. In fact, yeah, I guess Volodya has left, but you know, in Yang Mills' case, of course, you know, having a non-zero theta angle would be the one case one would like to consider. But I actually don't know in that case whether what happens to the lattice. Well, the thing is, you know, the lattice reflection positivity, even though heuristically it's very similar to the continuum reflection positivity, but it's still you have to prove that. So it's not an obvious thing. And I actually don't know what happened to the reflection positivity in the lattice Yang Mills theory when you turn on theta angle. But that might be one case to consider.
Yeah, there are other models also that people are very interested in, like the Hubbard model and so on, at finite chemical potential.
Right.
Which, yeah.
Yeah.
I mean, that would be really dramatic, right? Because people, let's say condensed matter physicists would really like to know what happens in the Hubbard model at finite chemical potential. And my understanding is that numerically they're stopped by the sign problem. So.
I see, yeah.
But Shiraz, the sign problem arises when you integrate out to fermions, let's say in QCD. But if you were to consider Schwinger-Dyson equations for closed and open Wilson loops, then perhaps this method of Xi and others can be applied to that. So there's no determinant anymore. You just have Schwinger-Dyson equations for open and closed Wilson loops. It's complicated, but can be done.
Yeah, sounds good to me.
Thank you very much for a very fantastic talk. Thanks a lot. Yeah.
Thanks, Ji. Thanks a lot.
Take care. Take care.
Yeah, let's thank him once again.
Thank you.
Thanks for having us.